What's going on, everybody? I apologize for my audio quality. I'm hoping I'm getting a new mic. I think I might have mentioned that in the other video, but I've recorded so many videos today, I don't even remember, so just throwing it out there. But today we're going to talk about our final concept in this chapter of organic chemistry. And you might be thinking, final concept? We just started this, and yeah, we did. I told you this chapter is going to be pretty short. Other than just kind of the practice outside of class you're going to need to do on naming some of the stuff, and I've already posted along with this video, there should be posted somewhere else, videos about naming examples. This is our only other concept. That's why we're testing pretty close. It's coming up soon. So our last concept is dipole moments. To start with our explanation, though, we're gonna back up to general chemistry, back into the chemistry class you had with me, or you may not have had with me. I want you to think about bond types, and if you can remember, what is the key factor in determining type of bond being formed? So take a moment and think about it, see if you can come up with it. If you paid enough attention, you would say electronegativity. Electronegativity was the tendency for an atom to attract electrons. We did a whole worksheet where you took these electronegativities and you subtracted the smaller one from the bigger one, and that helped you determine type of bond. So for example, fluorine and minus lithiums, 4 minus 1 was an electronegative difference of 3.0. That electronegative difference of 3.0 was enough to tell you it is an ionic bond. We're going to be kind of using that in a different way, though. So you're still going to have access to that table, but you're not going to be doing subtraction this time. We're going to be doing it to represent dipole moments. Dipole moments are a prediction of how electrons will tend to move in a molecule, not in a molecules. Think of it like it's a snapshot of a moment in time. If you remember, we predicted polarity in molecules, where we kind of looked and said, well, oxygen will tend to have the electrons more, or there was electrons on the outside of oxygen, so it's a polar molecule. Dipole moments are just a more complex version of that. So you're going to start by looking at electronegativities. Bigger the gap in electronegativity, the bigger the dipole moment in that bond is going to be. And then you'll draw net dipole moments by kind of figuring out how all of those arrows would combine together. You're going to add up all of the dipole moments and the directions they're going. If you plan on taking physics, you'll learn that this is called vector addition. It's a little bit weird, so just bear with me. I'll probably have a video going with this where I'll kind of explain it in a little bit more detail. So pictured here below are examples of how we kind of draw dipole moments. This is what a dipole moment would look like for hydrochloric acid over here, and one for water over here. So this one, hydrogen has a lower electronegativity than chlorine. So we draw our arrow with this little plus kind of sign to represent the more positive side, and then draw the arrow towards the negative side. And we do this little, I believe it's sigma is what this symbol is. This little sigma here is going to be used for partial charges. So this is not actually a positive charge because HCl is neutral, but it's slightly more positive on the hydrogen side, and it's slightly more negative on the chlorine side. And the how slight those charges are is based on electronegativity. So we would say the net dipole for hydrochloric acid points towards chlorine. This one's a little bit more complicated. Hydrogen and oxygens individually are going to point towards hydrogen to oxygen, but the sum of those two arrows together will actually mean that it's pointing straight up towards the oxygen. And this side of the molecule is going to tend to be more positive, and this side of the molecule is going to tend to be more negative. Like I said, I'll work out an example on paper of this and upload that with this video to kind of make it a little more clear. Dipole moments can actually be used to predict a whole lot of properties about compounds, as well as just predicting what they are. The most common one, and the one we're going to talk about, is boiling point. Boiling occurs, if you think about like subatomically speaking, when you make the intermolecular forces that are holding things together break. You tear them apart. So like water, for example, has hydrogen bonding. And you have to heat water to the point that those hydrogen bonds are no longer strong enough to hold the water molecules together, and they'll actually start floating away, and they'll start drifting around and become gas instead of a liquid. So this means that the stronger the forces inside of or between molecules, the harder it's going to be to break those forces. So if you have something that's polar, that means that those polar molecules will be attracted to each other and be more likely to stay together than those that are not. So a question for this could look something like this: which of the following would likely have the higher boiling point? They look exactly the same. The only difference is that on position number 2, this one has a methyl, and on position number 2, this one has an alcohol group. Well, based on what we just talked about, this one over here, this 1, 2, 3, 4, so this would be 2-methyl butane, or it actually goes by isopentane, but we don't worry about that. 2-methyl butane. It doesn't have anything that's really polar. The carbons and the hydrogens are all kind of getting pulled in directions equally, just like we had talked about before. Even though carbons are more electronegative, the hydrogens are all surrounding it, so there's no real negative area for it. Oxygen, on the other hand, has lone pairs of electrons and is quite a bit more electronegative than carbon. So oxygen is going to pull electrons a lot closer to it, meaning it's going to be slightly negative, and the stuff around it is going to be slightly positive. And that means that those molecules of this 2-butanol could actually get attracted to each other. And that means that they're going to have higher intermolecular forces, and therefore it's going to be less likely for them to boil at lower boiling points. You're going to need more energy to break that apart. And we can check, does this actually follow through in real life? And yeah, 2-butanol boils at 99.5 degrees Celsius. Meanwhile, methylbutane, or 2-methylbutane, sorry for that voice crack there, I'm making a bunch of videos already, boils at 27.8 degrees Celsius. That is a massive leap in boiling points. This also kind of explains why a lot of the stuff that we talk about in class has kind of can exist in gases, like methane, butane, propane, stuff like that. All of those don't have any polarity, so they're a lot more likely to have kind of weak intermolecular forces, and it's going to be a lot easier to have them exist as a gas. So that's, I'm pretty sure, all I got for this concept. There's going to be a worksheet that's going to involve you drawing dipoles and then making some predictions about some of the stuff. There will definitely be a short answer question about this on the test, and you'll get a kind of a feel for it based on some of the questions on the worksheet. I hope that's making sense for you guys. Watch the accompanying video to show kind of how I'm drawing them out, and you can get a better idea for that. In the meantime, though, this has been Mr. Diamond for this last short concept. I hope you have a good rest of your day, and I hope to see or hear from you soon. See you, everybody.